What we want to do now is exploit the fact that if you start drawing the gradient vectors near a critical point, the picture you get looks like the graph of a linear transformation. And in fact, the closer you zoom in, the more that graph looks like a linear transformation. Now, how do we tell that it looks like a linear transformation? We know from linear algebra that when you plug in the zero vector into a linear transformation, you get the zero vector. So there should always be a point where the vector is a dot. If you zoom in on a graph of gradient vectors not near a critical point, they all look parallel, nothing like a linear transformation. But if you're near a critical point, they look a lot like a linear transformation. Now, a couple little pieces of notation. With a normal linear transformation, right, we plug in the vector xy, and what we usually do is multiply by some matrix full of constants. Now, when we were graphing this, the vectors xy always started at the point 0, 0, and these aren't going to start at point 0, 0. They're going to start at the critical point. And what we do is, for example, what we're doing is we're going to plug in a vector xy. So let's just call, let's see, how about we do it this way? So you can actually see something that looks a little bit different. That's point 1 that looks directly away that way. So what we're doing is we're plugging in this little vector right here. It is going to be a tiny little vector. And so I'm going to label this as, say, delta x, delta y. And that's the vector that we're plugging in. So I'm not going to write t of xy when we're referring to linear transformations near critical points. I'm going to write down t of delta x, delta y. Remember, that's just a vector that starts at our critical point and ends at the point I want to draw the gradient. And so the equation becomes a little bit more complicated, but a little more descriptive as well, so I'm happy with that. Now, finding the ABCD is something that's actually a little bit harder than what we're going to do today. What we're going to do today is we're going to say the following. Ready? Since this vector points directly away, I can see that when I actually plug in this vector, the answer is just a stretched version of that. That makes this vector an eigenvector. For t, which is the function that draws all the gradient vectors near the critical point. Moreover, since it took the original one and made it longer and stayed in the same direction, that particular eigenvalue, whatever it is, I'm going to call it lambda 1, it has to be positive because it stays in the same direction but just stretches it that way. If you're at a minimum, you're going to be able to find a different vector, right? Well, hold on a second, let's do it this way, right? That you can plug in like this, and its answer is just the one stretched, right? So if I call the eigenvalue there lambda 1 and the eigenvalue here lambda 2, you can see that if this is a minimum, the eigenvalues are all going to be positive. Because every time I plug in a vector, the answer vector is going to be that same vector stretched in a positive direction. Now, if someone says, I don't even know ABCD, that's the cool part here, right? Is that if it's a minimum, all the vectors that we're plugging in get stretched in the same direction, but positive, right? So that's going to make the eigenvalues both positive. What happens if we're near a maximum? How does that change? Well, if we're near a maximum, it again looks like a linear transformation when we graph, but now I'm getting vectors that look like that, and vectors that look like this, and vectors that look like this, and this, and this, and this, and this, and this. Now remember what we're doing. We're plugging in a point. Now, for example, what point am I plugging in? I'm plugging, for example, that point in there, right? Where from here to here, remember this can be very small, right? This is going to be delta x. This is going to be delta y. And the answer, after we plug it into the linear transformation, is going to be this vector that's coming back this way. So what happens is, this is a linear transformation. That's an eigenvector because the answer actually stays on the same line that the original vector was, but now because the direction got flipped, we can see that the eigenvalue here is negative. That's going to be similar here, for example, when I plug in this point, right? We're actually plugging in this vector, and the answer stays on the same line, but comes back the other direction. So the eigenvalue here is also going to be negative. That tells us if we're near a max instead of a min, both eigenvalues, let's write it this way, both eigenvalues are going to be negative. And you can see the cool part about this is we have properties of this linear transformation that we see being graphed, and we don't even have the formula for it. Mathematics, this is very similar to what happens in a lot of mathematics. Right? We don't start with a formula. We start gathering properties together until we can actually come up with something. Now, the only other kind of critical point there is a saddle point. What happens if it's a saddle point? That color didn't work. Okay, if we're near a saddle, again, it's a critical point, right? But some of the vectors point towards, and in the last example, we saw this. This is very, very clear. And some of the vectors point away. Now, just a reminder of what's going on here. For example, here, to get this gradient vector, we're actually plugging in this vector here, and the answer stays on the same line and goes backwards. That means this eigenvalue is going to be negative. For this one, this is the point at which the gradient starts. So we're actually plugging in this vector here, that's the input vector, and the output vector stays on the same line but is stretched by some value. This eigenvalue here is going to be negative. So we see if it's near a saddle, one of the eigenvalues has to be negative, one of the eigenvalues has to be positive. And again, we don't even know the formula for the matrix. We just know from the picture that if it's a saddle, one eigenvalue is negative. That's this one and this one, because they stay on the same line, but the direction gets reversed. One of the eigenvalues is positive, because we can plug in a vector that stays on the same line, whose answer is on the same line, but whose length is just multiplied by some positive number. I didn't write that down right. What do you think? I think that's better. Good. I wrote down here right. So, yes. If we're near a saddle, yes, some eigenvalues are negative because those vectors get flipped and are still pointing back. Some of the eigenvalues are positive because those vectors stay in the same line and go the other direction. And now we have a complete description in terms of eigenvalues about whether we're near a maximum, a minimum, or a saddle using the gradient vectors. The next step is actually going to have to be talking about this matrix and then finding it.